Okay, this homework assignment is for RC circuits, and so for this problem, we want to find the charge enclosed on C2 at capacitor 2. C2 is just for capacitor 2. We want to find the charge after a really long time after the switch has been closed. So what we know is what they mean by a really long time. The switch is closed and basically its time goes to infinity. So as this switch becomes closed, they want to know what the charge will be at that capacitor. So some things to note, when we'll have voltages going through here and here, we'll have voltages going here and here, but after a while these capacitors will fill up with charge, and once they fill up with charge, no current is going to be going through here anymore. So the only current that's going through after time equals infinity is right here. Current is only going through here after a really long time, because this will stop the circuit once these two capacitors are filled with charges. So here we'll start the problem. So to start this off, we could use we can find because after time infinity we know that nothing's going through here, so we'll just think about these two, and since we know these two resistors are in series now because we're knowing this part, we can just add these two resistors together. So R1 plus R2 plus R equal. So 110 plus 220 should be equal to 330 ohms. Okay, so now that we know that, we know that's the equivalent resistance for this whole circuit right here. So now we can find the current that's going through this whole circuit. So let's just find using Ohm's laws and stuff, V equals R over I, and we know it's 12 volts, so 12V over 330 ohms is going to equal 0.036 amps. Okay, so that's our current I. That's 0.36. So that's our current going through here, 0.036 amps. So now that we know the current right there, we can find the voltage on the other side, because we know that voltages are equal to each other in parallel. So we'll know the voltage here and here, even though this was going at, like, after time goes to infinity, we'll know the voltages at R2 and R3. So we can just find that knowing the current. So we just rearrange Ohm's law again. So to find the voltage, it's V is equal to IR. But one thing to note, we want to find the voltage here. So since these two are in parallel, we'll use the 220 ohms resistor and find the voltage here, and that'll be the same because those two are in parallel. So 220 ohms times 0.0636 amps is equal to 7.92922 volts, equal to V. Okay. So now that we know that, we know the voltages are equal to each other in parallel. So now we know the voltage over here at time equals infinity, or after a long time after the switch has been closed. That's our voltage at R3. So once we know the voltage here, we can find the charge at C2. So for capacitors, the equation looks like VQ. So what we do know is capacitors have the same voltage, their voltages are equal to each other in series. So we know the voltage over here, so we know their voltages are equal to each other in series, so we could isolate for the charge. So what we're going to do is we're first going to add these two capacitors equal. We're going to add these two capacitors up to get a capacitance and equivalence. So I have C1 plus C2 and equals C equivalent. Now remember, you have to add the inverses. So 1 over 40 plus 1 over 80, and then you'll get some number, and I can do the math right here. So 1 divided by 40 plus 1 divided by 80. Oh, wait. You got 0.0375, and then just divide that by 1, and you'll get 26.6. I'll write it over here. 67 ohms equivalents. That'll be your C equal. And this right here is basically the same thing as taking the reciprocal if you added these two fractions and kept them as fractions. I just did 1 divided by the sum of those two, and that's basically the same thing if you flipped the reciprocal. So this will be your C equivalence for these two capacitors. So you basically, even though there's a resistor in between these two, you basically just added the two, and you got C1, 2. Ignoring the resistor in the middle, but you can do that. You can add capacitors in series just like normal, even though there's a resistor there. So you know that is that right there. And now all you're going to do, you're going to find the charge using, C equals VQ. So you're just going to solve for Q. So the capacitance is that right there. So 26.67 ohms. Ooh, that's not ohms divided by our voltage, 7.92. That's our voltage at that point, and that'll be equal to 2. I'm sorry. Actually, I wrote this equation wrong. And this one's wrong too. But the equation goes like this: CV equals Q. And now what we're going to do, we're going to multiply our capacitance, which is this right there, 26.67, and this is microfarads, times 7.92 volts. Oops. And that should equal, Q is equal to, and if you, well, this will be equal to 2.11 e to the negative 4 coulombs. Okay, and right here, notice that this right here, this is microfarads, but if you convert this to regular farads and then you multiply times the volts, that'll be your coulombs. So that's what I did right there. I just did an automatic conversion from microcoulombs microfarads to farads multiplied by volts, and that should give you the answer in coulombs. And now, since we know that this charge right here at C1 and 2, C1 and the charges are equal to each other in series, and as you can see, these are in series, so the charge is going to be the same. So at C2, it's going to be that answer. So that's how you solve that problem, and it's fairly simple. So yeah.